just replacing the first author, the lead of this work is Naila, who unfortunately couldn't make it. She's a student, PhD student in KAUST, and she couldn't take this long trip because of her little girl. So she put me in charge of this. And she's working with Bujama, who's a research scientist at KAUST, on on this framework of one-step ahead smoothing for filtering that I'll try to present it now. 2 points before I start. The sequence of the events, as I will show it, do not reflect the way we started looking at this. Actually, we started, we started working on this with Muhammad Al-Garamti before he moves to NCAR, and Bujama, where we were looking at estimating state parameters and parameters for subsurface hydrology. And in this community, they have what they call dual ensemble Kalman filtering, where they estimate the state and the parameters separately. They do the state first, the parameters first, they reforecast, and they do the state to improve the consistency between the estimates of the state and the parameters. So we started looking at this and see how they derived this approach, and we couldn't find a consistent Bayesian consistent way for this, and we derived our own. And then we realized that this could be interesting for filtering by itself. And then this led us to one-way coupled data assimilation system. What I call by one-way coupled assimilation, one-way coupled system is one system driving the other. Like the system that Lars was talking about, physics driving the biology are not affecting the physics. So the last 2-3 slides, you'll see something about coupling. At the beginning, it has nothing to do with coupling. Okay, so to start, so you have a state space model as usual, dynamical model, observations, and I don't need to remind you much about this. The Ensemble Kalman filters, why we like these techniques, robust, they are quite efficient computationally, and they are non-intrusive. The issue with them is that when we have, in large scale application, we have small ensembles. Model errors are very poorly known. Usually we neglect them, and we have nonlinear dynamics when the EnKF is built on Gaussian assumptions. So the background, the forecast error covariance can be roughly estimated by the EnKFs. And we have several auxiliary techniques, heuristic techniques to mitigate for these errors we're making on the covariance, on the background covariance matrix. So we do emulation, we do localization, hybrid formulation, some adaptive hybrid formulations, all these to mitigate on the errors of the covariance. The way we're looking at it is we're following a little bit what they are doing in the particle filtering people once they try to condition the sampling with the future observations. And for that, we'll use what we call the one-step ahead smoothing formulation of the filtering problem. So in the same way as when we expect the data to help the sampling of the particle filtering, we should expect also the data to help in the sampling in the EnKF framework. So how this works? When we do filtering, we do forecast, then we do analysis. And actually, it's not the only pathway to do to get from the analysis at time k-1 to the analysis at time k. So instead of doing the standard pathway from the analysis at the previous time to the analysis at the next time, passing by the forecast, you can do the same thing by doing a smoothing step first, then going to the analysis. Smoothing is that you go first, you use the future data, you come back, and then you do the analysis again. So as you do the standard pathway and you put yourself on a Gaussian linear framework, you get the Kalman forecast analysis. If you place yourself with the smoothing pathway, you start in the same way as with the Kalman. You do a forecast, but instead of going to the analysis, you smooth first, then you reforecast, and then you do the analysis. So what we're doing here, we're adding one more forecast step. In the linear Gaussian case, it should be exactly the same. You should get the same solution. So it's just a different pathway to compute the same forecast, the same analysis at the next time. but using the model twice and using the data twice, actually. So in the KF, you have one update and one forecast. In the KF, with one step ahead smoothing, it's still a filtering problem. We have 2 updates and 2 forecasts. But it's still Bayesian consistent. And when we started digging into this, from the dual thing, we found out the running in place algorithm from Kalman and Young in 2010, who had the same idea, but they were suggesting that it's empirical. Actually, it's not empirical. It's Bayesian consistent in a linear Gaussian system. So why we expected to outperform the standard filtering formulation? So it's in the same way, again, as I said, in the proposal density, or using future observations to help the sampling. Since we have a small ensembles, future observations should help us. So this should give us improved background that will likely give us a better analysis. And when you write the equations, you will end up, as usual, the model error covariance matrix will show up in the second update, but likely we're able to avoid this by computing the cross covariances between the ensembles from the second reforecast step, so what I would call. So this is what I was talking about. The one step ahead smoothing, there should be some relation with the standard proposal density. We didn't fully explore this, but using the proposal density to constrain the future data, this is another way to constrain straightforward to the future data without going through another, looking for another density. And we derived, so stochastic EnKF can be derived straightforward from this approach very nicely. To derive a deterministic version, we had to assume some assumptions and correlation between the pseudo forecast. What we call pseudo forecast is the second forecast step. It's not the real forecast because we used the future data and the observational errors. So we tried this on the, as usual, on the Learners 96 to experiments, 5 years assimilation window, and compared EnKF with EnKF with one step ahead smoothing. SAKE is one of these, it's like ETKFs, like AEKF is one of these square root deterministic EnKF methods. And we have 3 different observation scenarios. We observe half, all, and quarter of the variables. We assimilate every 4 time steps, and we, of course, use inflation and localization. And so for the results, you have the EnKF for all, the first column, all observations, assimilating half of the observations, and quarter, function of inflation and localization, the usual plots we do. And when we compare EnKF with OSA, one step ahead smoothing, you see a clear improvements. Here we implemented the filters with 20 members. And then when we go to deterministic, as you know, when we run with small ensembles, large number of observations, we get more, larger improvement with the square root filters compared to the stochastic EnKF. But the message is that whether you put one step ahead smoothing in the square root or in the stochastic EnKF, you see big, really interesting improvement. Now you will tell me that you see improvement because we're running we have twice the computational cost. We're running here with the 40 model runs for the one step ahead smoothing, while in the regular one we're running 20. So we compared with half of the computational cost. So here the figure is showing the ensemble size, the relative improvement between the one of the EnKF without one step ahead smoothing and with one step ahead smoothing with the light color, and with the darker color is half of the ensemble size. So both of them at the same computational cost, and yet still there we see some good significant improvement by running half of the ensemble but conditioning on the future. Okay, and when just as general result we get from all the experiments, we've done many more experiments, is that you see more improvement when we assimilate less data. There are less data in the system. And then when we use, when the background, there are more errors in the background, like small ensembles, when we neglect model errors. So when we put model errors, we don't account for it. We see also improvement by conditioning with the future data, and actually even with the small, with half of the ensemble size, so similar computational cost. So we took this system and we, quickly, 1 or 2 slides, we implemented it on a network system for surge forecasting in the Gulf of Mexico during Hurricane Ike. And what we did here, to be able to run the system with small ensembles and use the one step ahead smoothing, we implemented hybrid. So we can run a small ensemble and then use OSA, so we don't much increase in the computational cost. And quickly, the results are also in a realistic system. We see also kind of the same improvements. We compare here with, and again, with half of the ensemble size. So here it's 10, here is 20 ETKF. We had ETKF on the AdCirc, so we didn't bother. We just added one step ahead smoothing to the ETKF. And we have n equal 10 ensemble members and 20 ensemble members plus the static covariance. And so the same computational cost, and when you add one step ahead smoothing, you see really good, impressive improvements over there as well. So exploiting the future observations could help us, at least in the LORENZ 96, and in this example, to improve the ensemble background. It outperformed, in the test we made, the standard EnKFs for comparable computational cost. And we see particular improvements when there are challenging conditions, especially for the background covariance. And then the only issue we've seen is that when the smoothing window, when the frequency of the observations is too long between one observation and the other, where the smoothing step might not be efficient because of the nonlinearity in the, so the data should be close to each other within the linearity assumptions to make a good correction. Otherwise, you might iterate and go to what Geyer presented in the first day, and what the RIP does actually is iterate on these. It could help with intrite. Okay, so back to the original problem where we looked how this could work. How this could work with the for state parameters. So when we put it for the state parameters, we start from an ensemble of parameters and an ensemble of states. We forecast. We do smoothing for both. We reforecast, and we analyze the state only, because you don't need to analyze the parameters because it's a constant dynamics for the parameters, right? And so, as I said, we wanted to see how we derive a dual EnKF, and it's different in the dual EnKF because it adds a smoothing step to the state as well. In the dual EnKFs, they don't do smoothing to the state. When you write it in a Bayesian framework, you have to do smoothing to state, and it improves, actually. It brings a lot to the table, as you can see from this example from Mohammed, who did subsurface hydrology. He has hydraulic conductivity and head to estimate. And when we add this smoothing step to the state almost for free, you get much improvement just because it's derived directly from a Bayesian consistent framework. I will not bother much of this, but it gives a Bayesian consistent framework for the dual approach that is very heavily used in the hydrology at almost no cost, and it's Bayesian. So we take this same approach to the one-way coupled system. And what we care by one-way coupled, again, is the Zn, the second model, depends on the variable of the first model, and both models are observed. I can cite marine biology for this. We have a student also working on predicting oil spills. So you have images of oil spills, and you're also estimating the drivers of the oil, which is physics. So you can think about assimilation to coupled systems. So there are a lot of applications, all of them involving transport. So if you apply the same thing, we usually do classical solutions, strong formulation, when we put both of them in the same state vector, or we could do with them in a weak formulation, as has been presented by the first two speakers earlier. And we can do the same thing for OSA. So OSA, what we'll do, it will add an extra step, smoothing step for both states, and also an extra analysis step, but separate analysis step for each one separately. And we tried this on the on the coupled learn is 96, but to make it one-way coupled, we remove this term. So now it becomes one-way coupled. And with this, we have 144 variables, 3 years assimilation window, and we estimated every second variable, every 4 model step. We have a lot more runs, but I will show you just quickly what's going on. Now, since you have different dynamics, and we wanted to inflate, we didn't want to play a lot with the how to tune each localization scale for each system, because they can be different. So, and Shaidong Liu had introduced some way of do adaptive correlation, adaptive localization based on the some threshold of the correlations, and we implemented it, and it works actually very nicely, this approach, and it avoided, started scaling the localization up and down for each system. And with just one slide to show you also here that we see some very good improvements from compared to the regular EnKF. We have EnKF strong and EnKF weak, and the same versions for with one step ahead smoothing. And also here we see very good improvements when we put this one step ahead smoothing. So this OSA formulation is being proven so far very efficient, and it proves consistency mainly between the parameters and the filter, and it's the same way between the driving forces and the derived second model variables. So far, so good with this. So OSA is beneficial for strong and seems to be beneficial for strong and weak standard EnKF. Something we've seen is that the weak formulation works. Actually, it helps when you don't have a lot of members, because it avoids introducing some noise from the cross correlations that are not well estimated when you have a small ensemble, which makes a lot of sense. And again, we've seen improvement, much improvement when we have, when there are challenging conditions in the system. So what we're working on now, just to finish this, is Naila is working on implementing this approach with Dart, and hopefully she's telling me this should not be as complicated as we were thinking, and hopefully we'll next year we'll start testing it in a real MIT general circulation models of the Red Sea. So I'm done. Thank you very much. And if you